First of all, thanks to the organizers for this lovely meeting and for having me here. What I'm going to talk about is space-time singularities and space-time singularities in the context of quantum gravity. So in the classical theory for gravity, in Einstein's general relativity, space-time singularities like a Big Bang or a Big Crunch generically appear. Okay. So this is the content of the Penrose-Hawken theorems. Okay. And this is usually taken as a signal that a theory must break down whenever you have these singularities. And the hope is that maybe a quantum theory for gravity will eliminate these singularities. Okay? But we don't know yet what the quantum theory for gravity is. Okay? So there's no experimental evidence for quantum gravity. So it's just merely theoretical guesswork. And last time I checked, there was like 22 proposals mentioned on Facebook. On Wikipedia. Facebook, but there will be many more. And what I'm going to discuss in this talk is like two conservative approaches, which arise from just canonically quantizing general relativity. And these are the Wheeler-DeWitt quantization, or the Wheeler-DeWitt theory, and loop quantum gravity. Okay? And the loop quantum gravity community has recently put out a number of papers where they say that, in the Wheeler-DeWitt theory, you have singularities for a certain class of wave functions. Whereas in loop quantum gravity, these singularities are eliminated. So for them, that's a selling point for loop quantum gravity. However, there's an issue with these results because, well, they're derived within the framework of orthodox quantum mechanics. Okay? And there's some conceptual problems there. Okay, which I'll get to. And these conceptual problems are solved in the Bohmian approach to quantum gravity. Okay? And when you analyze the problem of singularities from the Bohmian approach, you find that, well, in the Wheeler-DeWitt theory, there may or may not be singularities. It depends on the wave function, the initial conditions. Whereas in loop quantum gravity, there's no singularities. Okay? And I can even show that for any wave function. Okay? These results in loop quantum gravity were only for a certain class of wave functions. When I do the Bohmian analysis, I can actually do it for any wave function. So what is this Wheeler-DeWitt theory? Well, that's just using the usual quantization recipes to general relativity. So these usual quantization recipes work really well in the context of high energy physics. So the guess is, well, or the approach is, well, why not try this to also general relativity and see what we come up with. And when you do that, well, first you start from the classical general relativity, which is about a space-time metric. It's about geometry, okay? And it's a four-dimensional metric, so space and time. First you go to the Hamiltonian framework, where you turn everything in terms of a dynamics for a three-dimensional metric, so a spatial metric that evolves in time. And then you quantize. And what you end up with is wave functions that are defined on a space of these three metrics. Okay? And you find a certain equation, a wave equation for this wave function. Okay? This is the so-called Wheeler-DeWitt equation. It says that the time derivative of the wave function is given by some Hamiltonian, some non-trivial Hamiltonian acting on the wave function. And in addition, this Hamiltonian acting on the wave function has to be 0. So this immediately implies that this wave function has to be static. It doesn't change in time. Loop quantum gravity, there's a very similar structure. It's again applying canonical quantization, but more or less in a different representation. And the states now become states on loops or holonomies, depending on the version. There's a number of technical problems, like regularizing this equation, finding solutions and all that. But there's also conceptual problems. So first of all, there's the measurement problem, which of course carries over from non-relativistic quantum mechanics. But in this context, it's especially severe, because you want to describe the whole universe, and there's no outside observers or measurements which could collapse the wave function. Okay? And second, there's this problem of time. As you saw, this wave function is static. It doesn't change in time. So how can we tell from this wave function whether the universe is expanding or contracting or running into a singularity? And thirdly, it's a question, what exactly does it mean to have a space-time singularity in the first place. Okay? You just have a wave function on these three metrics. You don't have an actual metric. There's just this wave function. So several notions have been proposed in the literature, like that the wave function has support on singular metrics, or that the wave function is peaked around singular metrics, or that an expectation value of the metric operator is singular. But neither of these definitions is really very satisfactory. Okay? So they might hint you some properties of singularities. But for example, if you look at the last one, it's an expectation value. So it seems like an average over an ensemble. So on average, then there is a singularity. So what does it mean then for our universe? Okay, that's unclear. In a Bohmian approach, there's more than just a wave function. Okay? So in the Bohmian approach, there's an actual three metric. And there's a certain dynamics for this three metric. And this dynamics depends on the wave function. Okay? Very similar to the non-relativistic case. And even though the wave function is static, this three metric, this actual Bohmian three metric, is generically going to evolve in time. So you can analyze just from calculating what this three metric is doing, whether your universe is expanding or contracting. And also, you can analyze the question of singularities. So you have an actual metric, so you have the same definition of singularities as in the classical case. Okay? So one important point is, well, in the context of non-relativistic quantum mechanics, we know that Bohmian mechanics reproduces the predictions of standard quantum mechanics. Okay? In this case, I can't really say something like that because it's kind of unclear what exactly the usual predictions of this really Witt equation are in the context of the usual quantum framework. Okay? To give an example, like there's a wave function that is well studied, the Hartle-Hawken wave function. Okay? People try to extract a lot of predictions from that. But if I look at that from the Bohmian point of view, for that wave function, I don't have an evolution. So my three metric is going to stay static in time. So this doesn't correspond to what we see, right? An expanding universe. So from the Bohmian point of view, this wave function would be no good. Okay. Before I go to singularities, there's a number of things you can do with this Bohmian quantum gravity. I'll just mention some of these briefly. There's the problem of quantum to classical transition in inflation theory. According to inflation theory, all structures are supposed to come out of vacuum fluctuations. Okay? And it's a question how these vacuum fluctuations turn into classical perturbations. Okay? You can nicely analyze that with the Bohmian approach. Okay? And you see very simply that you get this quantum to classical transition. Another issue is, or for some cosmologists, is with Boltzmann brains. If you have, if our universe stays dominated by the cosmological constant at late times, then there's the worry that so-called Boltzmann brains appear. These are disembodied brains just floating in the air, or into nothingness. And the worry is, well, if these Boltzmann brains keep, there's a certain worry, which I won't go into, that these Boltzmann brains keep appearing time after time. Okay. If you look at it from the Bohmian point of view, you see that these Boltzmann brains do not appear. Okay. So whatever the worry is, there's no worry in the Bohmian context. And then thirdly, well, you've seen this semiclassical gravity before in Max Tegmark's talk. So because full quantum gravity is so difficult to calculate anything, you go with a semiclassical approach where you treat gravity classically. And so in the classical Einstein field equations, you put in an expectation value of the energy momentum tensor operator. And this is going to be good if the wave function is approximately classical, or if matter is approximately classically. But if you have macroscopic superposition, you run into problems. And an alternative you can do is plug in an actual Bohmian energy momentum tensor. Okay? And in certain respects, this approach would be better than the usual approach. So here you have a practical tool inspired by Bohm. Okay, now turning to space-time singularities. Well, what these loop quantum gravity people did was like analyze simplified models of quantum gravity, where you assume homogeneity and isotropy, okay? If you do that, well, in the simplest case, you just have 2 degrees of freedom. Yeah. 1 degree of freedom is for gravity, so in the metric, so you have this A there, that's the scale factor, that's a positive number, and just tells you the size of the universe, okay? If it's growing, it's expanding, if it's decreasing, it's contracting. And the matter is by a homogeneous scalar field. So the scalar field is constant everywhere, it just changes in time, raises or lowers. And then the classical equations, what you get is that either the scale factor is static, so that's Minkowski spacetime, so no singularities, or you have a big bang or a big crunch, okay? So instead of using this scale factor, I also often going to use this alpha, which is the logarithm of the scale factor. So A is positive, so alpha can be ranges from minus infinity to plus infinity, and the singularity corresponds then with alpha going to minus infinity. So A being 0, that's the singularity, big bang or big crunch. That corresponds to alpha going to minus infinity. And in alpha phi space, these classical trajectories are like this, so straight lines, and alpha going to minus infinity, that's a singularity. So all these trajectories have a singularity. You can quantize this theory according to the Wheeler-DeWitt approach. Okay. You can do a Bohmian version of that. These are the guidance equations. Okay. And then it depends on the wave function whether you have singularities or not. If you have a real wave function, there is no singularities. For certain wave functions, you have the classical solutions. For other wave functions, you have both trajectories with singularities, like the ones on the left, these start with a big bang and end up in a big crunch. And these other ones are bouncing universe. They go from large volume to a minimal volume and then expand again. Okay, so here it depends. You may or may not have singularities, depends on the wave function and the initial condition. Let's get this. You can also do a Bohmian version of loop quantum gravity now. And just to make it really short, what happens now is that your wave function has support on just discrete values of the scale factor. So the scale factor can be 0, then a certain value, then twice this value, and so on. And if you do a Bohmian approach of this, you find that the Bohmian scale factor can only attain those values. So, okay, so the universe is a certain size, then at random times there might be a jump, jumps to a bigger size, might jump further or smaller. And then you can and there's certain transition amplitudes to jump from one scale factor to another scale factor, okay? And what you find is that there's a certain wave equation for that. If you analyze this wave equation and then calculate what are the probabilities to jump all the way to a 0 scale factor, so to a 0 volume, or what's the probability to start from a 0 volume and then jump to a non-zero volume, well, you can find then that these probabilities are 0. So what it means is you never have a big bang or you have never a big crunch, okay? So there's no singularities. And this is for any wave function, okay? So in summary, we can analyze the question of singularities in an unambiguous wave from the Bohmian framework. And in the Wheeler-DeWitt theory, indeed, it depends on the wave function whether you have or have not singularities. In the Bohmian framework, you do not have singularities, okay? Of course, this is a simplified model, and it remains to be seen what happens in a more general model. Okay, thank you.